Chapter 5, Section 1 and 2. I'm only going to cover one in this video. So we're going to recognize, write, and use trig identities, and we'll do some verifying. So to review some of our trig identities from last chapter, we should recall that the reciprocals are like sine is 1 over cosecant. We should be pretty confident with these 6 already. Pythagorean, I think some of you are still working on that. So where the Pythagorean theorem comes from, kind of give you some y to the identity. If we look at our unit circle, so our hypotenuse is 1, and we have our theta value here, or we'll call it u, like the identity here has it. The y value was like the sine, so the sine of u. The x value was the cosine of u. And so if you just apply the Pythagorean theorem, you take your cosine squared plus your sine squared, it has to equal 1 squared, which is 1. And so that's really where this comes from. Then quotient identities, which I think you're starting to get better at this, tangent sine over cosine, y over x, and then cotangent is just the reciprocal of that. So cofunctions. Now these we don't really know a whole lot about. I mentioned them in the past chapter, but we got to add some stuff to it here. So for all of these, our sine is pi halves minus u, tangent is pi halves minus u. So you have the pi's in all of these as well. And the pi halves is 90. So if you take 90 minus some angle u for these, it equals the cofunction. And where that comes from, if you're looking at the right triangle here, and we look at a sine, so sine of this angle would be equal to, we'll call this m over n, and then cosine of this angle would also be equal to m over n. So those would be the same thing. So if I call this 35 degrees, this would be 55 degrees, and so those two angles always add up to be 90. So these two angles always have to add up to be 90, and so the sine of one is equal to the cosine of the other, the complement. And so these would be called cofunctions. Even and odd kind of goes back to our symmetry from chapter 1. Our tangent has the odd symmetry, so does our sine wave. Our sine wave has symmetry about the origin, so you can have that rotational symmetry. And then cosine actually has the symmetry over the y-axis. And so look at the symmetry, you should see the even function, so cosine here would be even, and then odd for tangent and sine, or odd. And so you can look at the sines. If I'm given the sine of a negative angle, it's equal to the negative of the sine of the positive angle. And the one that's probably more powerful is the cosine of a negative angle is the same thing as the cosine of a positive angle. And so we can evaluate and solve some, and this is really a review of last chapter, where if we know the sine is 1/2, we know the cosine is positive, that information first just tells us that we're in the first quadrant. They're both positive, so all students take calc, we got to be in the first quadrant. So if I draw my triangle here, my sine of this angle has to be my opposite over my hypotenuse. And so I can use my Pythagorean theorem to do the 2 squared minus 1 squared and get the square root of 3 for this segment of the side. And so I want to find tangent of that angle. It's going to equal the opposite 1 over the adjacent square root of 3, which is the same thing as the square root of 3 over 3 if you rationalize it. And so that's really a review of last chapter. And then we can also find here sine of theta equal minus 1/2 equals 0. So if I first isolate my trig function, I get this. So then I have to think on the unit circle, where is sine 1/2? Sine is the y value, so I want a y value that's 1/2. So both of those segments would have a y value of 1/2, which are created from these two triangles. So we have a sine value of 1/2, a sine value of 1/2. So it's a small leg of the 30, 60, 90. And so this first triangle is the easy one, that's just pi 6. And then the second one here, it's the pi, or 180, minus the pi 6, so that would be 5 pi 6, would be the two measurements. So both of those would be the solutions to that equation. Okay, so simplifying. Simplifying is a little more difficult than verifying, because simplifying actually, you don't know what you're trying to get to. So you're trying to simplify it, but you don't know quite when you're done. So you need to apply your algebra and your identities to get a simplified form. And so for this one here, you need to realize that there's two terms right here. There's two terms. And in both terms, there's a cosecant, cosecant. So I'd factor out a cosecant x, and that leaves me with cosine squared x minus 1, which cosine squared minus 1, I know what that is. If you go to your Pythagorean identity, if I subtract 1, so I have cosine squared x minus 1, and then I subtract the sine, I find this equivalent form of Pythagorean identity. So I know cosine squared x minus 1 is negative sine squared x. So I can rewrite that as negative sine squared x, which just gives me less terms. But then I see that cosecant and sine has a relationship. Cosecant is 1 over sine x times the negative sine squared x. So then I can reduce a little here because the sine in the denominator reduces with one of these signs here. So I'm left with a negative sine x, and that's as far as I can take it. So that would be simplified. The hard thing again here is knowing how far do you need to go until you know you're done simplifying the problem. Verifying. Now, most students would prefer how to verify because now you know what you're trying to get. So I know this left side I'm trying to get it to become negative secant. So now I know when I'm done. And so to do this, I always want to look at the algebra. I try to use the algebra first. So I need to subtract these. To subtract them, I need common denominators. So I need to multiply this first one by 1 minus sine theta on the top and bottom. And then the second fraction I need to multiply by cosine and cosine. When I do that, my denominator is cosine times 1 minus sine theta. That's the common denominator. My numerator here, if I distribute this sine, I get sine theta minus sine squared theta minus cosine squared theta. And that's still I'm trying to get equal to negative secant theta. So then I'm trying to figure out, do I see anything that's occurring here? And I do notice I see a sine squared theta and a cosine squared theta, but they're both negative. So let's pull out, let's factor out a negative 1 from those two values. And that just changes the sign of those to both positive, which we should recognize that. Our denominator stays the same. And it's still trying to equal negative secant theta. So now I see that this quantity here is actually 1. So that's 1. So 1 times negative 1 is just negative 1. So I'm getting sine theta minus 1 over this. Now I'm almost seeing sine theta minus 1 and then a 1 minus sine theta. So those are almost the same thing, but they're opposites. So I'm going to factor a negative 1 out of that numerator. So I'm going to have a negative times a negative sine theta plus 1. So it just changes the sign of that quantity over cosine theta times 1 minus sine theta. That still equals negative secant theta. So now we actually have the same quantity. Even though it's written in the opposite order, negative sine theta plus 1 is the same thing as 1 minus sine theta. So those would reduce out because everything in this fraction is multiplication. So they have a negative 1 over cosine theta, which is a negative secant. So negative secant theta equals negative secant theta, and we are finally finished. So we have to factor at times. We did that a little bit of the last verifying problem. We got to do it again here just as a skill. So we should realize 1 minus cosine squared x, can you factor that into our two quantities? So the 1 times the 1, then a negative cosine x and a positive cosine x. So this is actually that difference of perfect squares when you factor that. And then this other one's like a trinomial, and if you need to rewrite it, so instead of writing cosecant x squared, we just write like x squared. If you factor this trinomial, this polynomial, it's the same as dealing with this trig trinomial, except that x is cosecant x. So if you want to factor the polynomial first and get like the 2x and x, and then for the signs, we know they have to be a negative and a negative because they multiply to be positive and add to be negative. And then we're trying to figure out these the OI. So 2 times what number plus 1 times what number would equal to negative 7. So 2 times 2 would be 4, and then the 3 times the 1 would be 3, and 4 and 3 is 7. So I can rewrite that, and instead of using x, I'm writing that with cosecant x. Everything else in the factoring is the same thing. So if you want to rewrite the polynomial to help you out, you can. So rewriting not in fraction form. These are just some skills we're going to be using as we verify the factoring and then rewriting in not in fraction form. To do this here, I notice my denominator is a binomial. It's kind of, we've done this before with the difference perfect squares with our radical denominators. So let's multiply top and bottom by what we used to call conjugate here. So 1 plus sine y. It's like the difference perfect squares. We multiply top by 1 plus sine y. So this algebra skill we've seen this before. And so our denominator becomes 1 minus sine squared y. Our numerator, I'm not going to multiply, I'm going to leave it cosine squared y times 1 plus sine y. And then we should see that this denominator, 1 minus sine squared, is an identity. And it comes back to the cosine squared x plus sine squared x equals 1. And so 1 minus sine squared x is going to equal cosine squared x. So this quantity here is the same thing as cosine squared x, which we have, or y in this problem. And then so we have cosine squared y there and there, so those reduce out, and we just get 1 plus sine y. And so it's no longer in fraction form. It's the binomial. That's all for 5.1. 5.2 is a separate video you can watch now.